Hello everyone and welcome to the channel. Today we will be talking about a very interesting topic and it's one of my favorite topics in exoplanet science. I am very excited to discuss this paper with you. So without further ado, let's roll the intro and pose this video's question. Let's start with a few basic concepts that will help you appreciate this paper even more. Firstly, how do planets have magnetic fields? Well, two factors play an important role here. The presence of molten metals like iron and nickel in the planet's core and the planet's rotation. As the planet rotates about its axis, the molten metals swirl and generate electric currents. These electric currents, which are basically moving electric charges, generate the magnetic fields for the planet, a well-known phenomenon in the field of electromagnetism. Secondly, why is a magnetic field important for a planet? Well, there are two main reasons for that. The magnetic field protects the planet from the energetic particles released by the host star. Earth's magnetic field shields its surface from the highly energetic particles such as protons flying from the sun as a solar wind. The energetic particles have the potential to erode the planet's atmosphere as well. The best example for this is Mars in our solar system. So you can see why an exoplanet's magnetic field is an important attribute to study about. Detecting an exoplanet's magnetic field will hint towards its interior activities and help us determine whether it has an atmosphere or not, which will then be directly connected to its habitability. With the basic concepts out of the way, let's dive into today's paper. In 2003, Shkolnik, Walker and Bohlender released a paper where they presented their results about detecting planet-induced activity on the chromosphere of this star. Through their observations and analysis, they determined that the activity was due to the magnetic interaction between the planet and the star. Since the planet-induced heating is confined to a narrow region on the surface of the star, the increased activity can actually track the planet and the activity's period would equal to that of the planet if it is a magnetically induced activity. This was monumental because it was for the first time that scientists could indirectly get information about an exoplanet's magnetic field. Theoretically, the magnetic interaction between the planet varies as 1 by d squared. This is the graph that you get when you plot the inverse square function. So clearly, you can see that as the orbital radius of the planet increases, the force of interaction reduces rapidly. Hence, the authors chose the tightest of systems to study. Also, since the planet will be close to the stars, it is expected that the magnetically enhanced activities will be observed in the outermost layers of the star, primarily the chromosphere. These are the planets that they selected. Please note that the last two stars, Tau Ceti and our Sun, are chosen for reference purposes. Now, temperatures in the chromosphere can usually reach up to 20,000 Kelvin, and activities in this part of the star are usually observed in the UV region of the electromagnetic spectrum. This region is not observable by ground-based telescopes due to the Earth's atmospheric interference. Hence, we need to look for other indicators. Stars whose spectral type is lower than F, so stars in this region of the HR diagram, are observed to exhibit chromospheric emission via calcium-2 H and K lines at these wavelength values. Calcium-2 means that these lines are observed from singly ionized calcium atoms, that is, calcium atoms where one electron has been ripped off. These lines are sensitive probes of temperature and electron density. This is an example plot of these lines for our main star itself. Due to the broad absorption and the fact that the lines are observable from the ground, these lines are an optimal choice for monitoring chromospheric activity. The authors obtained high resolution and high signal to noise ratio data through 3 observational runs at the Canadian France Hawaii telescope with the Gecko spectrograph. The 2 stars that I had mentioned before, Tau Ceti and the Sun, were considered as reference stars that do not have a close-in planet for comparison purposes. These are the results of their analysis. The x-axis for this graph is the wavelength axis. For the top panel, the y-axis is the mean absolute deviation, a statistical quantity used to measure the dispersion or a spread of values of each data point from the mean of the data. The top panel basically shows how much the data points are deviating from the mean, or the average, specifically for the calcium to H line at 3933 angstroms. You can see that there is a large deviation at that particular wavelength, indicating increased activity. The bottom panel are the residuals, which are plots generated by subtracting the data from model spectra. These plots were used for generating the MAD plot of the top panel. The second plot here demonstrates the deviation for every star considered in the dataset, and you can see that there are enhanced activity in that particular wavelength. The bottom two panels are for the reference stars, Tau Ceti and the Sun. Now I know the Sun doesn't have a giant planet close by with a magnetic field. The increased deviation observed there was due to coincidental sunspot activity, which the authors confirmed after consulting the Michelson Doppler imager on board the Solar Heliospheric Observatory or SOHO. So you can see that stars with close-in large planets exhibited increased chromospheric activities. A strong coherence between the deviation of the H and K lines can be observed in this plot here for each star. Now one question that can arise is that how do we know whether this activity is not due to stellar surface activities? Well, the authors observed that the MAD value for another strong line, the aluminum 1 line, was very low, further strengthening the reasoning that the observed activities were due to magnetic interactions between the planet and its host star. This entire analysis was the first indirect glimpse of a magnetosphere of an exoplanet. So what other criteria do you think is crucial for an exoplanet to be habitable, and how would you go about observing and analyzing that? Please leave your thoughts behind in the comments. I hope you enjoyed the video and the discussion. I hope you learned something new. Please like the video and share it with your friends and family. And please subscribe to the channel. Thank you and stay curious.